This presentation shows you how to analyse a design with Tolcap, how to do it, when and why, by which we mean what you get out of going through this process. We will work through a simplified example which sets out to show how to analyse the components of a design using Tolcap and how to calculate a stack tolerance. But it also shows when to use Tolcap, which will turn out to be as early in the design stage as possible, and how Tolcap raises questions about the design, questions you need to address with your supplier to help ensure you have a sound design. Here's the example. It's a camera of some sort, and it has three components: a heatsink, a body, and a lens. The table shows the dimensions and first cut tolerances in the stack that defines the image distance in the camera. The heatsink dimension, 3 mm plus or minus 0.05, is the height of a raised platform for a photodiode array that is connected to a surrounding printed circuit board. The body, which is 12 mm long, plus or minus 0.01, just spaces the lens from the photodiode array. The lens is injection molded PMMA. The front part of the lens is 7 mm plus or minus 0.1 from the mounting shoulder of the body. Accepting the assigned tolerances, the distance from the front of the lens to the image on the heatsink is 22 plus or minus 0.16 mm worst case. We may root sum square the tolerances and say the stack dimension is 22 plus or minus 0.11225. Okay, 22 plus or minus 0.11. But is root sum squaring valid and meaningful? Anyway, the component tolerance is achievable. Let's use Tolcap first to estimate CPK for the assigned tolerances. So open Tolcap and log in. In the process group, select casting, select precision pressure die casting for copper alloys, check we're on the tolerance tab, enter the dimension as 3, and for tolerance plus or minus 0.05, and click calculate CPK and ppm. There's no prompt to select the material because this map is specific to the material of the part, and there's no modification required in either the geometry or variation wizard. But CPK is an acceptably low at 0.69. So let's find the capable tolerance. Click the CPK tab, select 1.33 as the target CPK, click Calculate Tolerance and ppm. So to achieve CPK, we find we need the minimum tolerance estimated is plus or minus 0.08 millimeters. Next, analyze the body. Select machining and turning and boring. Make sure we're back on the tolerance tab. Enter the dimension of 12 millimeters and tolerance plus or minus 0.01. Click Calculate CPK and ppm, and the predicted CPK is 1.64. But we need to click the material drop down and select copper alloy, non-ferrous copper alloy, and the predicted CPK will fall to 1.4. Next, click the geometry wizard. The body starts as a casting to save material, so it has to be turned round at some point in the machining process. So specify one additional setup operation and click Apply. The predicted CPK is 1.29, which is close enough to 1.33 to be considered an acceptable design. To analyse the lens, select Plastic Moulding and Injection Compression, PETP, Filled, PF, PMMA, etc. Get back on the Tolerance tab, enter the dimension as 7, tolerance 0.1. Click Calculate CPK and ppm, and CPK is 2.34 so far. Next, click the Geometry wizard. The characteristic is across the parting line, which it wasn't on the heatsink, so select Yes and click Apply, and the predicted CPK falls to 1.22. Next, click the Variation wizard. Does the need for optical properties impose any limitations on material flow, etc.? Oh, I don't know. Never mind, then let's select Yes in the last question just to be on the safe side and click Apply. And the predicted CPK falls to 0.66. We'd better find a tolerance that gives an acceptable CPK. So select the CPK tab, set the CPK target to 1.33, click Calculate Tolerance and ppm to find that the tolerance should be at least plus or minus 0.16 millimeters. So now we've analysed each component using TOLCAP, we can update our assembly drawing and our table with tolerances which will be capable to CPK equals 1.33. Now with these capable tolerances, the distance from the front of the lens to the image on the heatsink is 22 plus or minus 0.25 millimeters, worst case, the 0.25 being the sum of the tolerances. The root sum square of the tolerances is 0.18. Using the formula derived for CPK equals 1.33 tolerances, T stack is 3/11ths of the sum of the tolerances plus 8/11ths of the root sum square of the tolerances, we get T stack is 0.198 0.2 plus or minus. This design example is presented to illustrate how to use TOLCAP and how to calculate a stack tolerance. That said, it also serves to highlight when to use TOLCAP and how it can improve the design process. The example is presented deliberately as a diagram to show you that TOLCAP is best used early in the design process. It's hard to overstress this. Once you've got to a drawing, you're committed to some concept, and it's very difficult to backtrack if you find you've got some problems. Then don't just look at the CPK values or the tolerances you get from TOLCAP. Look at the processes you've selected and the answers you gave in the wizards, because this can steer your design and your project, as we shall see. Let's consider the lens first, as it required the widest tolerance. Does the requirement for optical properties really affect process capability? An obvious question to ask the supplier, who may have evidence that it doesn't. Then again, is dimensioning to the front of the lens avoidable or even appropriate? If it is, consider mounting the lens somehow inside the body onto the front face so that the dimension of the thickness of the lens is on one side of the die. But look at the optical equations. Of course, the thickness of the lens will have an effect on its focal length, but maybe the shape should be adjusted and the optical centre brought in line with the mounting feature. Review the optics and the sensitivity to dimensional errors. The design assumes that a raw cast heatsink will be satisfactory. It may be necessary to machine the casting anyway to clean up the faces to mount the sensor. But machining is also a way to get better tolerances if it's necessary to improve the stack tolerance. The camera body tolerance is an order of magnitude smaller than the other components in the stack, so this may be an opportunity for cost reduction. Do we really need to machine the casting? Is there an alternative process that might produce the part at lower cost? The objective of this example has been to show you how to analyse a design using TOLCAP and how to calculate a stack tolerance. You should do this analysis as early as possible, right back in the concept stage of the design, and use its results in discussions with your supplier to make sure you're going with the processes you selected and to get the best out of your design. Before we close, I'd just like to tell you the story of this example. Of course, it's set up for the objectives I've described. Why else would we have a copper alloyed camera other than to show you that for some processes we have different maps for different materials and others we have one map and a material correction factor. but it was based on a real case. The organisation concerned were just rolling out Tolcap, and I was invited to a meeting where the design team were presenting the concept of such a camera to the production people. Well, they were very concerned about the distance between the lens and the sensor and that the image should be in focus. And they were describing some design whereby there would be an assembly fixture and all the parts would be held in place and a light shone through onto the sensor and some measurement taken to show it was in focus, and then shims would be fitted and glue. And as you can imagine, the production people were getting quite agitated about this. I asked to take the design away and I applied TOLCAP in just the way we've done it. And to honestly my surprise, when I put in CPK equals 1.33 capable tolerances for each component, the stack came out entirely within the requirements that the design team wanted, leading to a very simple assembly. And I tell you this for two reasons. Again, to underline that you should do this design analysis very early in the concept stage, and two, just to say that just occasionally TOLCAP gives you a solution rather than a list of problems of capability issues. Thank you for your attention. We hope you found these presentations of value. For more information, including blog articles, answers to frequently asked questions, pricing, and how to sign up for a Tolcap account, please visit our website at www.tolcap.com.